right, this is Honors Algebra 2 Pre-Calc. We're doing section 2.7 in the Pre-Calc book, which is actually part of our chapter 6/partial fractions unit. So we're going to complete the partial fraction decomposition for the rational expression x plus 7 over the quantity x squared minus x minus 6. So in this situation, we're not just setting it up, we're finding the value for the constants. So the first thing I always have to do is factor this denominator. So my original denominator is going to factor into an x minus 3 times an x plus 2, right? And that's important that we know how to factor because, again, you're kind of dead in the water if you can't factor. And when I do my setup, because both of those factors are linear, I'm going to end up with a fraction where the x minus 3 has an a on top of it and the x plus 2 has a b on top. So it's a sum of those two fractions, right? Again, it doesn't matter which one you put first. It doesn't matter what letter you put over which one. What matters is that in the end, you end up with the same number on top of the x minus 3 that I get on top of the x minus 3. You don't have to use a and b. You could use q and j. You could use your initials. Just don't use x because there's already an x in the problem. And in general, O's frequently create problems. Okay, so this is my setup, right? I have to do the setup first. So just this piece, right? Just this is my setup, right? You can't do anything if you can't get it set up properly. So setting it up is important. My next step after setup, and actually I'm gonna rewrite this step so that you can still see the setup, even though I wouldn't if I were doing this on like my own test or something. So I'm gonna rewrite this. I wouldn't naturally like normally rewrite it, but I'm gonna rewrite it so that we can still see the setup. So my goal now, and actually let me rewrite it with the factored form because there's no reason not to. So it was an x minus 3 times an x plus 2. Okay, so now what I want to do is get a common denominator, but it's important that that common denominator is identical to this original denominator, right? So I notice that the x minus 3 fraction already has the x minus 3, but is missing the x plus 2, so I'm going to times by x plus 2 on the top and x plus 2 on the bottom. I notice that the x plus 2 fraction already has the x plus 2, but is missing the x minus 3, so I'm going to times by x minus 3 on the top and the bottom. And what you'll now notice is that all of my fractions have this same original denominator, which means I'm basically cleared to ignore it. Again, if that really bothers you, me saying ignore it, you could multiply the entire expression by that big blob of math, by x minus 3 times x plus 2. That's fine. Either way, you're basically getting rid of them, and you're at the point where x plus 7 equals an a times an x plus 2 plus a b times an x minus 3. Now I'm going to show you two different ways to solve this. I'm going to show you the clever substitution way that I did in example 3 and that I advocate for most of the time. But I'm also going to show you another way, and it's actually the way that I learned in high school and did for years until someone showed me the clever substitution idea and my mind was blown, and now I do that. So let's start with the clever substitution idea. The clever substitution idea is that you're going to say, what would make this thing equal 0? Oh, x equals negative 2 would make this thing equal 0. So what I'm going to plug in is I'm going to plug in x equals negative 2, because again, this equation has to be true for every x ever, because we're saying that this fraction will literally always equal these fractions, right? So I'm going to get a negative 2 plus 7 equals a times a bunch of 0, which all gets knocked out, right? Plus b times a negative 2 minus 3. Right? So I'm going to end up getting 5 equals negative 5 times b. Oh, look, my b is a negative 1. All right. I then am going to do the same clever substitution, same idea, but with this other term. So I say, what would make x minus 3 be 0? It would be a positive 3. So if I plugged in a positive 3, that's going to knock out this b term and let me solve for the a term. So I'm going to get 3 plus 7 equals a times 3 plus 2 plus b times a bunch of 0, which is totally going to get knocked out. So I get 10 equals 5a. Oh, a must be 2. So I could, from there, finish my problem out. I could totally finish the problem out, and if I did, what I would do to finish this problem, and I'm going to slide this over here for a sec, right? What I would do to get my answer is I would take my original setup, right, and instead of having a over the x minus 3, I would put a 2 over the x minus 3, and instead of having a b over the x plus 2, I would have a negative 1. So my answer is going to be a 2 over x minus 3 plus a negative 1 over x plus 2. Now, I would suggest you leave it this way. There's always somebody that says, well, couldn't I make this a minus in the middle and then make this a positive 1? And the answer is yes. However, the word of caution I'll give you is that later, when this numerator might have a binomial, if you factor the negative out, the negative affects literally everyone in the numerator. So if this numerator is just the 1 by itself, then moving the negative in front is totally fine. But if the numerator has multiple terms, let's say the numerator is a negative x plus 7. When you yank that negative out, you not only affect the x, but you also affect the 7. So just be mindful that the reason I prefer this answer, I think that by not changing it from a plus sign in the middle, you make fewer risks in terms of making silly mistakes. Now, before we wrap this example, I do want to show you that there is another way to get these same two numbers. So notice that we got that a was 2 and b was negative 1, right? So I'm going to erase this and I'm going to show you there is another way to do this. So the way I actually learned to do this in high school, I learned that you go ahead and clean this up and distribute. So I'm going to get x plus 7 equals ax plus 2a plus bx minus 3b, okay? And then the way I learned in high school is that if these two expressions are equal for all x, like genuinely every single x ever, then that means that the components on the left-hand side and right-hand side have to match, meaning that the x terms on the left-hand side, which is just 1, there's only one x, have to equal the x terms on the right-hand side. Well, if you look at the x terms on the right-hand side, right, so I'm going to put the x in red, the x term on the left-hand side is x, which is just a 1x. The x terms on the right-hand side are ax and bx, meaning a plus b. Well, that gives me an equation. 1 equals a plus b. And the same thing has to be true of the constant terms, right? The constants on this side, well, there's a 7. And the constants on this side are a 2a minus 3b. What this gives me is a system of equations that I can pretty easily solve for a and b, but you'll notice that this is much harder than the clever substitution option. So what I now have is I now have a system of equations. I have a system of equations that I could pretty easily use elimination for or substitution. So what I'm going to do is I'm going to times the entire top system by negative 2 to get negative 2 equals negative 2a minus 2b on top of a 7 equals 2a minus 3b, and now when I add straight down, I get I get a positive 5, right, because negative 2 plus 7 equals a negative 5b. Oh, look, that means negative 1 is my b, right? Which is the same answer I got using clever substitution, but seems a lot harder, right? And then I would pick either of these two equations to plug back in. I'd probably go ahead and pick the first one because it's easier. 1 equals a plus a negative 1. So, oh look, 2 is my a. And you see that I get the same two answers. Now, you might say, Hogan, once you showed us clever substitution, why on earth would we ever pick this method? And that's a good question. The honest answer is that there are going to be a few problems where this is going to bail you out of a problem where clever substitution doesn't work. The clever substitution usually doesn't work when you have repeat factors. So we haven't seen any like that yet in examples where I actually made you solve for the value. But it can, well, repeat factors or quadratic factors can also create some problems. So actually, the quadratic factors are largely the bigger issue because, for instance, if you were trying to plug in to make x squared plus 1 equal to 0, you'd have to plug in something with an I, and you really don't want to have to do that in these problems. So essentially, if your factors are all nice and happy linear factors like a problem like this, you wouldn't pick this option. But as we move forward, you're going to see a couple options where sometimes clever substitution leaves you only knowing one of the variables and you need to find two others or something. So this is just an extra tool to kind of keep in your toolkit so that you have an option if we come to something harder later.